Hi. So, in the last lecture we have been discussing more about how GPU warps are formed and they are scheduled inside the SMs. In this current lecture we will be focusing on one of the very important topics relevant towards optimizing GPU programs, and this is memory access coalescing. So, before getting into the detail of that, let us first do a small recap on the hierarchy in the GPU memory, how the different memory segments are organized, and how really global memory is accessed by the computing threads inside an SM. So, as we have discussed earlier, inside when a kernel launches, essentially a grid of thread blocks are launched. Multiple blocks can reside inside one SM as decided by the high level scheduler of the GPU, and it depends on the size of the blocks. One thread block cannot be split across SMs, and so when a set of blocks get mapped to a set of SMs, I mean in this example we are just showing a single block mapping into a single SM like that. So, essentially I have a set of threads inside the block which are computing, which are being packed by the low level scheduler of the SM into the units of computing called warps, and each of these warps perform they actually progress through the instruction sequence atomically, so that I mean all the threads inside the warp are executing in lockstep with respect to the instructions. So, here we have just shown this earlier picture actually, that how each of the SPs or the scalar processors are getting mapped to the threads, and they are executing the threads, and of course we will have scenarios where we have more number of threads rather than the number of SPs. So, that would require another lower level of scheduling of the threads on the SPs, and that is how things are done as discussed earlier. Now, whenever the threads while executing an instruction, they will require access to the global memory. So, they would definitely require two kinds of access. They would need to bring operands from the memory, and they would need to write back updated variable values to the memory. So, this essentially should be happening through the hierarchy of the GPU, the memory hierarchy of the GPU. So, every access should finally all the variables have their locations in the global memory, and also while you have written the program, if there are certain constant factors in your program, you may have mapped them also into the constant memory for faster access, right. So, when a thread is asking for a variable's value, it may possibly be residing in the L1 cache, or it may be or the L1 cache part or the shared memory part, or of course, if you are lucky, then it may be residing in the register file segment allocated for the thread. Otherwise, the thread has to access this value from the global memory. Now, of course, by standard computer architecture techniques, as we know, that register access is fast, shared memory access is a bit slow with respect to the register, but it is the global memory access which is a lot slower, because essentially this is outside the SM units, outside the entire GPU's compute environment. It is in the DRAM chip of the GPU. So, accessing the global memory is an order of magnitude slower. So, if you are writing a program which will be doing lot of access to the global memory, essentially your program's performance will be low. It will not execute with high throughput. If you can somehow rewrite the program so that effectively the number of global memory accesses are getting reduced, then your program will perform much faster. So, essentially the important thing here is how I can reduce the number of times global memory is going to be accessed by a program. Now, this question leads to a lot of memory related optimizations, some of which will be touching throughout this lecture sequence here. Now, of course, you can understand that if we are going to reduce the number of accesses a program makes to the global memory, we need to somehow optimize the accesses and make data resident in the shared memory and the register file, the shared memory or the L1 cache, whichever way it is getting configured as discussed earlier. And so, we have to optimize the program in such a way, maybe at the source level. So, First of all, let's review the scope of computation for the different threads. So, you have got these different SMs. Each of the SMs have got their own, as we discussed earlier, each of the SMs have got their segment of registers which are dedicated for them. Each of the SMs have got the memory partition, the internal memory partition into the L1 and the shared memory segment. And then through the interconnection network, you have access to a unified L2 cache, which accesses the banked global memory through the memory controller, right. So, for each thread doing its computation, it has got its own separate private memory segment allocated in the global memory, which is also called the allocated in the DRAM, which is known as the local memory for the thread. For every thread block, you can as a programmer define an amount of shared memory which is available to the thread block for doing its computation. So, since it's shared memory, so all the threads executing the block will have a consistent view of the variables in the shared memory, which again means if thread I and thread j belonging to the same thread block are executing and thread I makes an update on a variable, it is immediately visible to the any other thread j. This updated value is immediately visible since it's in the shared memory. And of course, you have multiple kernels, and in case you are executing concurrent kernels, which is a feature supported by modern versions of CUDA, so you have that would actually mean multiple kernels executing together, and they can have their part device access to the global memory. So, now coming to the important question of the latencies of these accesses. Now, they definitely differ for different memory spaces as we discussed earlier. So, this is a nice summary here that the global memory, which is accessible by all the threads, is the slowest, definitely it is in the DRAM. The shared memory, which is divided into each of the different SMs, it is accessible by all threads inside the thread block. It is much more faster, order of magnitude faster with respect to the global memory. However, if your variable is resident in the registers, then its access time will be the fastest. So, this is the order which is standard like any computer architecture. Now, the question is how really is the global memory accessed by the threads? We have already discussed that the threads are packed together into what we call as warps, right. So, when these warps are executing, the GPU, whenever the threads inside a warp are looking for data to be accessed from the global memory, the GPU tries to gather the accesses together and form specific access instead of accessing per thread, the GPU would try to merge the accesses together into global memory accesses. So, and this is known as coalescing. So, the GPU coalesces this global memory loads and stores depending on whether threads inside a warp are looking for data sitting consecutively in the memory or not. So, in a summary, I would just say that the global memory is coalescing the GPU is coalescing the global memory loads and stores. Now, these loads and stores requests are put up by the warp, the threads inside a warp. And so, if I have multiple threads inside a warp which are looking to access global memory locations which are consecutive, they would be packed together into a single global memory transaction. So, of course, we have to define what is a global memory transaction, what are the data points that can be brought together by a single global memory transaction and all that. So, suppose you have a warp where all the threads, you have 32 threads, and the 32 threads are, the warp is executing a load instruction or a store instruction. In general, let me call it a transaction. So, essentially, you have got 32 memory requests issued in parallel, right. So, if these requests are actually going to be for consecutive positions in the data space, that means you have 32 aligned 4-byte words which have been requested. Now, this is exactly what is defined as a global memory transaction. So, a global memory transaction is essentially a transaction in which from the global memory you can bring 32 cross 4 number of consecutive bytes from the global memory. So, that is the width of a global memory transaction. When you are accessing the DRAM chip, definitely this is how the hardware is optimized. The hardware designer knows that the global memory access is slow. So, he is trying to provide the programmer an optimization that, okay, whenever you access me, the access is slow, but I am allowing you to access lot of data points in parallel by giving you a wide bus. What is the width of the bus? It's 32 cross 4 bytes. That would mean if in a warp you have 32 consecutive thread IDs and they are making a load request for 32 consecutive memory locations, essentially you have to do a single global memory transaction. So this is the most fundamental and important thing here. Since your global memory access width is 32 cross 4 byte, if a warp is looking to access 32 consecutive memory words, memory locations, so essentially we are defining each memory element as a 4 byte word, let's say integers. So you can access the warp can access its corresponding instruction, corresponding data points from the memory using a single global memory transaction. Now, as we discussed earlier, since these global memory transactions are slow, overall objective here is to reduce the number of transactions by different warps which are executing across the SMs. So for that, what is required is you should be able to write the program with very efficient, what we call as memory access expressions. So whenever you are accessing an array position in the memory, you have an access expression. So just to give an example, suppose you are trying to access M is an array and you have a expression here which is telling that for current values of I, j and k, this is the location you want to access, and you put it in some variable a. So then the access expression would be this. So as a programmer, you need to define very nice access expressions, so that you have to define them with the global memory optimization in mind, so that overall when your program executes, you have less number of global memory transactions, so that the warps do not need to wait too much for the memory operations to be done, both loads and stores, and so that the overall progress is much faster for the kernel. Let's look at some examples to make this idea very clear here. So consider the execution of this very simple program. So we have this small kernel here. So it's just a memory access kernel. So you are first computing the thread ID using this expression, standard expression of block dimension multiplied by block ID plus the thread ID. Everything is in the x direction. So considering single dimensional kernels, single dimensional blocks, and single dimensional threads. Single dimensional arrangement of blocks and single dimensional arrangement of threads inside block. So this is your TID, and all that you are doing is, for every TID, you are accessing the corresponding TID indexed location in the array A. So let's say this is your warp 0. So for this warp 0, you have got the consecutive thread IDs, and we are just taking an example here. So you have, let us say, this 8 threads executing inside warp 0. So when this line of the code is executed by all the threads inside the same warp, what really happens? What are the memory elements that are accessed? So as you can see, by looking into the access expression, so this is your expression which says that you just access the memory location corresponding to the TID. So warp 0 contains TID 0, 1, 2, 3, 4, 5 and like that. So warp 0 is accessing memory locations A0, A1, A2, A3, A4, A5, A6, A7 like that, right? So considering that this is going to be your global memory transaction, we are not drawing here 32 thread IDs and all that, just to make the point very clear. So essentially, what are you really doing? You can have a single global memory transaction for this read operation. Here is a simplistic example again. We are assuming that the global memory transaction width is 32, is 8 cross 4 bytes. Just assume that. We are not drawing 32 TIDs and all that here. So essentially, I have one global memory transaction for which will suffice for doing the read operation for all the thread IDs here, right? Why? Let me just repeat again, because as we discussed that the global memory access is quite wide. Assuming that in this case the global memory access is defined as 8 cross 4 bytes, that many bytes, 32 bytes I can bring in parallel. So essentially for this specific case I can bring in all the data points required for executing this line. I can do the corresponding load operation here by a single global memory transaction. So essentially the global memory transaction would be defined based on the width of the warp. As we have discussed already, since standard warp width is 32, the global memory transactions can be done in such a way that you can bring in 32 cross 4 consecutive bytes from the memory together, right? So assuming here for our simplistic example, I mean we have these many threads and you are bringing in the corresponding data points, you can bring all of them together in a single transaction. If I just want to generalize this, all that I would like to do is put 31 here. So this would go up to 31, this next would start from 32 and this would go up to 63 and like that. We are just taking a simplistic example here. We are just considering that the warp width is 8 and similarly the global memory transaction is also 8 cross 4 bytes, right. So here we can see that since all the accesses are consecutive locations in the memory for the threads executing inside a warp, I can have one transaction for doing the read and then there will be an execution of the increment operation and then again there would be one transaction for updating all of these locations by another write operation for the global memory, through which all these locations will be updated in parallel, because again the locations are consecutive. So what happens if the program is a bit different? So just continuing with the animation for this program, you have warp 0 executing and bringing everything together with one global memory read followed by one updating everything here in one global memory write. Then again bringing together all the data points through one global memory read and again updating everything from this using a one global memory write. Similarly for warp 2 read and write, and that's how things will go on. Now consider a small difference here in the program. So let's look into the earlier program once again. So earlier program was this, ATID is ATID plus 1. In this program we are providing an extra parameter here, access with offset, and the offset value is S. So you compute using normal notions the TID, and then what you do is you do the access for a TID plus SH location, right. So what you are doing is you are accessing the TID plus SH location, adding it up and then updating again the TID plus SH location for the array A, right. That is what you are doing. Now let us see how it goes. So in terms of the reads, what is happening? Consider the S value as 1. Now that would mean if I again start looking into warp 0, with thread ID 0, I am doing an access of A1 location, right. So earlier it was this, the access was this, but now the access has kind of changed, right. So you continue like this and TID 7 is looking for A8. So overall with this change, what is really happening? You will have the first transaction for locations and in the next transaction you just bring A8. So this together gives you 2 transactions. I hope the point is clear here. Again I have got 8 threads inside a warp. They are looking for 8 data points to load, to update and to write back. However, the problem is the access here is offset, in the sense that the access is not properly aligned here, right. So, when the access would happen for this memory, although these are consecutive locations, but fundamentally if you look into our definition of the access, what did we really want? There has to be 32 aligned 4-byte words, right, or in this case by the WARF definition there has to be 8 cross 4 bytes byte aligned access, but the alignment is wrong here, right. Essentially here what's happening is you have got an access of consecutive locations, but the access is starting from A1. So, also the entire thing is not aligned with the WARF, right. So, that would actually lead to 2 global memory accesses here. I hope this is clear. So, essentially the DRAM bandwidth is utilized with respect to the warp's width. If the warp's width in this case is 8, so the accesses would be, so like when I am defining the access will be aligned at the positions where it is basically so the first row can be done through a global memory transaction. So, as you can see in this picture, the memory organization is shown with respect to this access alignment, right. So, the moment I put in the offset, the alignment is lost. I mean, so in the first access I can only get things from A1 to A7, because in if I am looking for data from A0 to A7, they all come inside the aligned access, but A8 cannot be aligned, I mean cannot be brought in with A7 in one access, because when I bring A7, the aligned access is being in terms of the warp width times 4 number of bytes. So, it will actually bring in data from A0 to A7, from which actually A7 is only useful for me. So, for the next thing I will require another access, right. That is why when I go for A8, it is a different access here. So, overall I would have 2 different global memory transactions for the read operation, and again I would have 2 different global memory transactions for doing the write operation. So, just the introduction of this offset, I mean of course the offset introduction is not, I mean it may be required, right, depending on the program that you want, what you have a desirable property for the program. If this is what you really want as your access pattern, then you have the following problem. So, essentially the number of global memory transactions, earlier it was for this entire operation, for executing this line of code, every warp was spending 2 global memory accesses, but now instead of 2 they are spending 4 global memory accesses, right. So, immediately you have lot of slowdown in terms of execution time of each of the warps. So, I hope this point of access alignment now becomes clear with this example of offset. So, just to summarize again, we showed the earlier example where all the accesses are nicely aligned, because we have the warp width times 4 bytes. So, that is the definition of the global memory transaction, and that is essentially one of the important points here, that the warp would request 32 aligned 4-byte words. So, one transaction, each of the transactions would happen in spaces of this 128 bytes, considering warp width of 8, warp width of 32. But whatever is the warp width in your system, multiply that by the requirement of the integer storage, that is 4 bytes. So, that is basically the unit of global memory transaction, all the global memory transactions are essentially aligned with those weights at that with that amount of width here. So, whenever I am doing this transaction, I am getting everything in a single transaction of the global memory, whatever is the requirement here from A0 to A7, because they have a nicely aligned access here. However, whenever I have a offset based code, then comes the problem here, right? Simply because the accesses have to be aligned with the warp width. So, here in this case, for this kind of an arrangement, I have the first global memory access for the warp 0 can only, it cannot form a global memory transaction starting from here and looking up to this. They have to be aligned at the warp width times 4 number of bytes. That is why it will have to make 2 transactions. The first transaction will bring in this many data, out of which this many would be useful. Again, the first transaction would bring in this many data, out of which only this many would be useful. The second transaction would actually bring in this entire row, out of which A8 would be useful. So, 2 global memory transactions. I hope that provides the summary of this thing, but overall we can see immediately what is the performance loss here. And this is how it will keep on going on. Now, consider a different type of access pattern. So, in my earlier access pattern, it was all with respect to offsets. I am doing a plus S here. Now, we consider what is defined as strided access. So, this is another kind of access pattern which we often see in our programs. Essentially, all I am doing is there is another integer parameter S, and whenever you are accessing the locations in the memory, you are multiplying the thread ID with S. We can see such patterns in very simple, normal programs that we write. So, this is one of the patterns, that is a strided access. What would it really mean? Consider again our simplistic example with warp width 8 and global memory accesses happening in 8 times 4 byte width, of course, and those accesses are aligned with this width. So, consider that S value is 2. Now, if S value is 2, I can see that for warp 0, the total number of accesses are actually spread across 2 rows here in our picture, right. So, for the thread ID 0 to 7, I am going to actually access locations A0. I do not want any access to location A1, because thread ID 1 is going to access A2, thread ID 2 is going to access A4, thread ID 3 is going to access A6, and like that, right. That is how it continues. So, in this case also, with S equal to 2, the number of global memory transactions required for executing this entire instruction for entire program line would be that I require one read and one write with respect to the program, but it will actually transpire to 2 global memory transactions for the read and 2 global memory transactions for the write operation. But what happens if I increase S? Consider S equal to 4. Now, things are further catastrophic. For warp 0, again considering 8 threads inside warp, look at TID 0, it is looking for accessing A0, but what about TID 1? Since S equal to 4, it is going to access A4. So, overall now the access is spread across this entire memory block, right. So, for the 8 threads, each of them are accessing a position shifted by 3 from the earlier thread, right. So, you are essentially accessing A0, A4, A8, A12, A16 like this up to A28. So, essentially since the accesses are again aligned with that restriction of warp width times 4 number of bytes, that is this much is your access alignment. So, essentially for covering this entire segment of the global memory, you would need how many? You would need 4 global memory transactions for the read and 4 global memory transactions for the write. So, as you can see, this is from a performance perspective for the program, this is going to be a impediment, I would say, because whenever you are going to have strided access, you need more number of global memory transactions for both for read and write, and strided access is something that we often do in our normal programs, right? So that's not something that we can do away with. So we have to figure out ways in which the program may be written in an alternate way, such that I can create an equivalent program where the accesses are intelligently managed. So these are the important performance impeding factors whenever we are writing code, which is going, for the GPU, and you have to write programs where you have a variant of the program which actually minimizes these accesses, or maybe it helps in coalescing the accesses. That means the program is such that the warp actually is looking for accessing consecutive memory locations which can fit in inside a single memory transaction. This is known as memory access coalescing. With coalesced access, you can reduce the number of global memory transactions, and that's going to be a very important performance factor for your GPU programs. With this, we would end this lecture. Thank you.